I'm Daniel Levine, and this is the Bio Report. With the mapping of the human microbiome, a new understanding is emerging of the complex relationship between the microorganisms that live in the human gut, skin, and elsewhere on the body, and the role they play both in disease and in maintaining health. Along with growing concerns about drug-resistant bacteria, this is giving rise to opportunities for narrow-spectrum antibiotics. We spoke to David Martin, founder and CEO of AvidBiotics, about the problems of antibiotic resistance, the benefits narrow-spectrum therapies offer, and how the sequencing of the microbiome is leading to new approaches to not only treat infectious diseases, but other diseases not traditionally thought of as being driven by microorganisms. Dave, thanks for joining us.
You're more than welcome.
We're going to discuss your company, AvidBiotics, and its efforts to develop a class of highly targeted antibiotics. But I thought perhaps we could begin with the recent effort by the White House to release a 5-year plan to combat the problem of antibiotic resistance. How big a problem is antibiotic resistance today, and how concerned should people be?
It's a big enough problem to attract the attention of the president. That's unusual, I think, in life sciences, and certainly I think it's unprecedented in at least my recall of any major politician like our president of the United States coming forward and saying we have a problem and we need to address it, and here are some resources and let's see a plan. So I think it's quite significant. There are a lot of numbers that are thrown around, most of which are accurate, but they're in many ways confusing. The CDC in Atlanta published a monograph at the end of 2013 describing the threat of antibiotic-resistant bacteria to the U.S. population. And they picked 3 organisms that were the biggest threat, but then the list goes on. And the problem is that while antibiotics are clearly the most important pharmaceutical or drug ever invented and marketed, because they've saved enormous numbers of lives and limbs, enabled surgery, for example. We would not have surgery today if it were not for antibiotics. It would be too dangerous. But the problem is that there are 2 unexpected consequences of antibiotics. The first one was not unexpected because Ian Fleming, in his Nobel Award lecture or presentation in 1945, I believe, described penicillin resistance that was likely to occur, and he'd seen it in his laboratory. So we've known about drug resistance starting with penicillin. So the problem with the drug resistance is that it's rapidly spreading, and that's interestingly for 2 reasons. One is you put a lot of antibiotics out there in the environment, in food, in people, etc. And bacteria are very capable of developing resistance to almost any chemical or drug to which they're exposed. But more of a problem, and it has been recognized recently, is the fact that bacteria share drug-resistant genes with other bacteria. So they're transferring these genes that encode resistance to bacteria among themselves all the time. And the other subtle part of that is that the genes of antibiotic resistance, or the genes encoding antibiotic resistance, travel together as a flock. So that if one acquires a gene that results in resistance to penicillin, one may also acquire a gene that conveys resistance to azithromycin. So what happens is that if there is antibiotic in the environment of a bacteria, for which the bacteria has a resistance gene, it will retain that gene, otherwise it's going to die. And the phenomenon then is it may retain the gene for that antibiotic, but 5 or 10 other antibiotics at the same time.
Well, coupled with the growing problem of resistance, there has been this significant drop-off in the drug industry's interest in developing new antibiotics. What's been responsible for that?
I think it's economics, purely economics, within the pharmaceutical industry. That is, antibiotics are successful many of the times, unless the organisms that one is trying to kill has resistance. And as a result, the course of an antibiotic successful treatment may be a week or 2 weeks. And it's not something that is going to be chronic, long-term therapy like for a viral infection or for lifestyle improvement or heart disease or CNS disease, where the patient, once started, may well continue on therapy for the rest of one's life. And so the duration of therapy is less, and therefore the profits are less. And people have, all of us have become accustomed to antibiotics being very inexpensive because so many of them are generic. So there's not the incentive to develop antibiotics because it costs essentially the same for the pharmaceutical industry to develop an antibiotic as it does, say, for a cardiovascular drug that requires continued use by the patient for the rest of one's life. And so they have invested their development dollars, their discovery and development dollars, into other types of drugs.
This is an interesting times in terms of science. Efforts to map the human genome have now given rise to mapping the microbiome. We're coming to an understanding of the complexity of the relationship between the microorganisms that live in our gut, skin, and elsewhere in our body, and not only for diseases, but for wellness. How is sequencing the microbiome changing not only the need and ability to develop narrow-spectrum antibiotics, but the development of and understanding the role that these microorganisms play in diseases not even traditionally thought of as bacterial diseases?
That's a very interesting point. The Human Genome Project was responsible for fostering and essentially pulling the development of new technologies for very rapid deep sequencing. What that has enabled over the last 7, 8, 10 years is the sequencing of, for instance, the gut microbiota by simply sequencing the DNA of all the bacteria that's in feces. As a result, we have discovered how complex the gut microbiota, or the microbiome, and those words are used interchangeably, but they shouldn't be. The gut microbiome is essentially the collection of all the genes within the microbes of the gut, for example, whereas the microbiota is actually the collection of the bacteria. But even today, we cannot culture more than 15 to 20% of all the bacteria in our gut. We don't have the tools or the know-how to culture them on petri dishes. So the sequencing has allowed us to identify how many different bacteria are there just by using a tag that's characteristic of each of the different species of bacteria or even strains. And that then has enabled the recognition of associations, if you will, between the presence or absence of certain bacteria in, for instance, the gut, and specific diseases or disorders. That is obesity, for example. And the difficulty is that most of those are, quote, associations, end quote. That is, it's not yet clear for the majority of them whether the presence or absence of the bacteria is causal for the disease or the disorder, or whether it's a consequence, or whether it's just random. So we're in a situation now in which we're able to generate, as it is called, big data on the genes of bacteria in our gut, in the vagina, on the skin, in the mouth, etc., and certain associations. What we need is the ability to prove or disprove causality. Is the presence of this bug or the absence of that bug causing a particular disorder or disease?
Well, let's talk about avidicins, the class of drugs you're developing. What are avidicins and what makes them attractive?
Avidicins are sort of a trade name that we have given the engineered bacteriocins that we are using to kill very specific bacteria. And these are derivatives of natural products that bacteria have been using for 1 billion years. They are complex proteins. Bacteria encode these complex proteins in their own genome. And when they're stressed, they release these R-type bacteriocins to go kill, if you will, the barbarians at the gate. They're trying to eat their lunch. We've learned how to retarget these very narrow spectrum proteins so that we can point them at bacteria that are not naturally targeted by these bacteriocins and kill them. And we can kill them in a highly specific manner. So this then becomes quite interesting in the context of both the emergence of resistance to bacteria, to antibiotics, in that if we can kill a specific bacteria and not put any pressure on the already insensitive other bacteria to gain resistance to, say, a traditional antibiotic, then we can kill a bacteria or a bacterium that is not going to spread any resistance that it might acquire. We're taking the selective pressure off of a bacterium so that it doesn't retain any genes that it has that cause resistance. This also allows us to do something else that traditional antibiotics have not been able to do, and that is to, for instance, subtract a very specific bacteria population from the gut without damaging the rest of the gut, which is so important for good health and so important to keep our gut from being invaded by disease-causing bacteria such as cholera or enterococci or Clostridium difficile. So these are agents that we are now producing and headed towards a clinic with, initially focused on it preventing and treating Clostridium difficile infection, which, according to the CDC, is one of the 3 major threats to the U.S. population. It's the most common cause of an infection in hospitals, more so than MRSA now. It killed, in 2011, I think, was the last time the data were accumulated. It kills about 30,000 people a year. and infects about 500,000 people a year, most of them in hospitals, and most of them develop this infection because they've been treated with broad-spectrum antibiotic, and antibiotic damages the gut microbiota, and it becomes sensitive to this invader.
Well, your pipeline right now is preclinical. It consists of a number of targets you might expect to see on the list. But what is the thinking in terms of priorities, and when do you expect to advance to the clinic?
Our first priority is an agent we have that kills all of the so-called hypervirulent or epidemic strains of Clostridium difficile. And we anticipate being in the clinic next year, towards the end of the year. We're just optimizing our production systems currently. This is really active. We've shown it works in mice that we can infect with C. difficile. It can prevent there being infecting, and it can prevent them from getting an infection if they are carrying C. difficile but not symptomatic. So we're held up towards putting this as a prototype into the clinic. We've shown in mice that we can administer this agent, which we call Avidicin CD, in the drinking water of the mice and not have any measurable impact on the healthy bacteria in a normal gut. So we're quite excited about this, if you will, laser that we can use, or sniper that we can use to subtract a specific bug from the gut and not damage the healthy microbiota.
You're also developing a group of drugs you call mycoside proteins. What are those, and how do you expect those to be used?
The mycoside proteins are immunotherapeutic molecules that we're developing for cancer. And the only relationship with the avidicins is that in both cases, these are proteins that we have engineered based on nature's successes to target very specific cancer cells, or in the case of avidicins, very specific bacteria, and kill them once they bind to them. So this is a technology that we've been working on sort of cryptically for a number of years, and we've had some significant advances in the last 6 months, so that we have animal efficacy studies in mice with transplanted human cancer cells, and we can show efficacy. And we're completing our preclinical activity and beginning to focus on how to manufacture these proteins, with the intent of probably using them eventually in collaboration, if you will, with the so-called checkpoint blockade drugs that are doing so impressively well in various cancers, particularly in bladder cancer, melanoma, and lung cancer. So this is a new class of therapeutics for us that we already have issued patents on it, on the platform.
You're also looking at food safety and animal health products. What are the applications you're pursuing there, and how far off do you think those are from commercialization?
Well, we have a very significant collaboration with DuPont for the use of our R-type bacteriocin technology to make what we call puricins that are structured like the avidicins, as a food safety product that would be used to spray on, or as a dip for food such as chicken, for example, to kill salmonella, or on dairy products to kill Listeria monocytogenes. DuPont is very active with us in this field, and the anticipation is that they will take the first couple of products into the marketplace in the not too distant future.
If I remember correctly, you've avoided venture funding. Given your biotech pedigree, I don't imagine it would be difficult for you to raise venture money. How are you funded? And if this is a conscious strategy, what was the thinking?
Well, the thinking it was interesting. From the beginning, Jim Knight and I, who co-founded the company with Jeff Miller at UCLA as an academic, decided that we were going to focus on bacterial diseases. And as a result, we felt that we could do a few experiments, what we call killer experiments, test our hypothesis. If it worked, we would raise a little more money just to go to the next killer experiment and work our way up without having to raise a lot of money, only to find that the concept or hypothesis was not valid and it failed, and then be sitting on other people's money trying to decide, gee, do we give it back to them, or do we go become a specialty pharmaceutical company and in-license a drug so that we could just sell it? And as a result, we decided we would just raise small amounts of money a bit at a time, and in addition, maintain control of the company. We certainly have had offers from venture capitalists whom we like. What we did not like is the terms of their investment. They have traditionally, as a group anyway, always wanted to have control of the company. And Jim and I felt that we had enough experience, so we didn't necessarily need a venture capitalist or several venture capitalists sitting on a board making decisions for us. And we have managed to be successful with a limited number of qualified investors, a couple of whom are venture capitalists who put in their own pocket money, not firm money. We have been very successful with a number of grants, small business grants mostly, from NIH. And we have investments from the venture capital arms of DuPont and now Merck. It was originally Cubist. Merck acquired Cubist early this year, and Merck is now an investor. So we have funded the company that way and have an easy time making decisions, put it that way. It's always scary to make decisions when you don't have anyone else to blame other than yourself, but Jim's office is next door to mine, and I can sort of yell even with my door shut, and we can make a decision.
David Martin, CEO of AvidBiotics, and listeners attending Bio 2015 can hear David on a panel discussion on redefining infectious diseases, bacteria, and health and sickness, June 16th in Philadelphia. David, thanks as always.
Thank you, Danny, for your interest.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.